Okay, hello class. We are actually, in this module, I want to do several assorted topics. And you can read more about them in the book, but we're not going to tie this to chapters or sections from the book. So I'm going to give you some talks based on my research or invitations I've had to give a workshop on optimization. And we'll do one talk per video. Each one is introducing a topic that I think is a really important topic that I want you to know, be familiar with, but you don't have to know it to the extent of cranking away computations for a homework problems or algorithms in the book. So the more big picture ideas and exposure here. So that's what you're trying to do, is sit back and take as much in as you can. Okay, so I'm going to share the screen. And the first talk is one I gave a while ago for an undergraduate workshop at NC State. So some introductory ideas. And we'll get to some pretty neat ones by the end, some advanced ones. But let's, this was again for undergrads who've never done any optimization. You're well past them at this point. But let's suppose you wanted to minimize this function of 5 variables. First things you notice, nonlinear, lots of nonlinearities in there. You don't know any optimization, but someone's like, you got to do it. I'm going to give you $1 million. Tell me your answer. First of all, there's 5 independent variables affect a 6th one. So this is an R6 space. So you can't do a lot of the graphical methods that we've done. Again, not much about calculus or optimization. What are you going to do? Well, I think it's pretty straightforward what folks would do. Some math. So you could just guess and check, plug in values for x1, x2, x3, x4. Function evaluation, see what you get, and just keep on doing this. And you could do it in a brute force systematic way. You guys now know enough programming, no problem. You could program this in MATLAB and go over this, a grid search over this, right? In X, if it was just x1, x2, that's a grid in the xy plane. At x3, now we have these layers. Well, same idea in higher dimensional hyperspace. Okay, so this is that function. And we'll just talk about some vocabulary based on that. Like, we know our local min and global min, but there's also things called saddle points right there. Many algorithms converge to local extrema or saddle points. And there's actually a whole class of problems where you're interested in finding those saddle points. We've spent all of our time optimizing, so we're not really looking at those, but just know they exist. And good places to look were tangent planes and horizontal tangent planes, or critical points. Those will find local extrema and saddle points. There's a d-test, the second derivative test. Global extrema, remember those occur from the extreme value theorem at critical points and boundary points. So if there's some region over which you're looking, like maybe right here, there's a region in the xy plane, and over that we're interested. Oh, right, this is just an R3 function, so it's not the one from the previous page. This is just another interesting function example to go over these terms. And then we've used the gradient in this class. And we've talked about that is the direction of steepest ascent, and the negative gradient is the direction of steepest descent. Just reviewing again some vocabulary types of problems we've looked at. Unconstrained optimization. Here's a nonlinear unconstrained. We've done constraints. Often we have these non-negativity. We haven't done these. And in fact, these can't be dealt with. You can't use the simplex. This makes a harder class. And so usually, do they really need to be strictly greater than 0? Could they be greater than or equal to? Or they could be greater than or equal to 1 or 0.5. Usually go back to the modeling there. We've talked about over a rectangle, constraining you to live on a line. The visualization of this, remember in R3, this is a circular paraboloid facing up from the origin. This is a vertical plane that slices through that, and you want the min, that is the intersection of the vertical plane and the circular paraboloid. And we learn a lot of things from the extreme value theorem in calculus 3 and talk about the existence of, do these things exist? We've also talked in this class, we've spent most of our time on linear programs, but here's just a little bit of ideas for nonlinear programs because they do exist. Most things though, in practice, if you have a nonlinearity in your program, you can often approximate it with a linearity. So think about how a tangent plane can approximate that nonlinearity within some region. Is that going to be good enough? So often what you do with nonlinear is to turn them into linear. And there's strategies for doing that. You looked at some in chapter 4. But suppose you had the nonlinear, you couldn't do anything about it, you have to keep it in there. Well, one thing you can do is do gradient descent. Remember, if you were wanting a max that's the same equivalent as negating the min, gradient descent would say the visualization is you're dropping a bunch of parachuters down onto this surface on a cloudy day. In higher dimensional space, you can do the same thing, drop them down in that problem before, 5-dimensional input variables, dropping down over a grid over that region or randomly, and letting them walk in the direction of gradient descent if we're trying to find a min, if we're trying to find a max, and the positive gradient. So each one's going to land somewhere on this surface or hypersurface. You can easily get a gradient then if you have an explicit representation of your function like we did on the first slide. Even though we're in higher dimensional space, we have an explicit representation. We could take a derivative and point in the gradient, go a few steps, get a new gradient, go a few steps, and keep on going. Another hill climber lands over here, gets a gradient, and he keeps on adjusting. They'll all radio back where they get once they have converged, and they'll all be converging to a local extrema. You pick the one with the biggest. And so the gradient is first order information with the first derivative, but you could also use information from the second partials. And some algorithms use that. That's in a matrix called a Hessian. Maybe you've seen that in some advanced linear algebra classes. So there's ways in which you can improve the algorithm by looking at not just your first order information, but also your second order information. Okay, here's just some ideas. So there was a particular code called gradient descent.m. You can search in MATLAB for ways for handling nonlinear programs. There's also one called fmin search and fmin. Check the help on those. But here's the questions you should ask when you have an iterative algorithm. You know, does it converge? Can you prove that it converges? Are there certain values of the parameter that make it easier for you to prove that it converges? Often, you're never going to be able to prove it converges in general, but maybe you say, for this special case, I can say this, for that special case, I can say something else. And then you should also ask about the rate of convergence. How many iterations does it take on average? Is it ON? Is it ON squared? Even if you can't say those things, can you demonstrate on a bunch of numerical examples, either synthetic and artificially generated or realistic ones? What is the standard problem size of n equals 100? Takes this many iterations, this much time. Are there things that you can do? Maybe the starting point, like if you initialize the algorithm a certain way, does that affect your convergence? What's the worst case analysis? What's the best case analysis? So you may be making algorithms higher by someone that you have to, you can use standard off the shelf algorithms, but often what you have to do is customize them for your particular problem that's going to make it run faster or more efficient. And these are the questions you should ask. Okay, so again, we talked about that there could be global, local, stationary points, or you could get to none of the above. That's that case. Most optimization algorithms, you know, unless you're working on a nice class, you can't guarantee convergence to a global min, much less even a local min. That's even hard to guarantee. But there are some classes, again, we've seen those, linear programs, certain cases of binary integer linear programs, and then convex programs we've talked about. Like here's a classic convex optimization that every local extrema is a global extrema. Those are great. But the good news is, even on really tough optimization problems, even though you can't say theoretically some nice convergence things, they often perform. Remember, think back to the simplex, like theoretically that had exponential worst case behavior, but in practice it's linear. So often that's the case, though, you're going to perform really, really well on most problems, despite a lack of convergence theory. Now, if you're an academic like me, that can make it challenging to try to publish something, an algorithm like that. Sometimes you're going to run into referees that are like, yeah, but you haven't proven this or proven that. And so you have to, often in those cases, to get it, if you can't prove it, can you prove a special case again? Can you show numerically? That seems to work really well. And often you have to just qualify the statements or the answers that you give. So don't think about academics and publishing, just think about your client. Like you have to come to them and say, here I did get an answer. And this is, I can't prove anything about it, but I can tell you this is the best we've found to date. Like this is a classic problem. No one has gotten an answer better than this. Like that happens for the traveling salesman problem. Okay, then we'll skip this. I don't think that's not related. Oh, okay, so then the next thing, there are some problems for which you can't get a gradient. Maybe you don't really have an explicit representation of the function like we did on that first slide, where it has some non-differentiable parts or non-smooth parts. Like that was a smooth surface that in R3 that I showed before, but there could be places where it just like, it's piecewise defined or it just juts off and there's a cliff. And so those are non-differentiable points. So I can't take the derivative to do all these methods that are built on the gradient, like the gradient descent method. Well, if that's the case, there are other methods that don't require the gradient. And there's also some line search methods, but there's also something that's really powerful called the method of alternating variables, or sometimes it's called coordinate descent. In this case, you're going to solve a series of one-dimensional problems. So let's just take a simple case where I have just an x1 and an x2. Then that creates another variable z, so you're actually in three-dimensional space. Now, what you can do though is say, suppose x1 is fixed at a value of 2. Then I'm going to try to optimize over x2, the other variable. So I've got two-dimensional space, two axes here. So if x1 is fixed at a particular value, it makes it a much easier. It's a one-dimensional problem. You'll solve for an optimal value of x2 given that x1, and then you'll take that value, fix that as your x2, and solve for x1. And you keep flip-flopping like this. So a series of sequential one-dimensional problems. And amazingly, that works really, really well for most problems. And what it would look like on a contour map, again, if we had that surface lives over an XY plane, well, the contour map is in the XY plane. So let's just focus on an XY plane here. And this is the XY plane in two-dimensional space. Well, that means the movement towards the optimal, the global extrema or local extrema that you're working in must move in perpendicular fashions, right? So it's only moving, I'm fixing one variable, and so I can only move in one direction, then I fix the other one, I move in the other direction. So I'd be doing something like this, moving in this rectilinear fashion. So keep that in the back of the mind. Like that is if you have a really tough problem, that's helped me out a lot. Like I'll show you a couple other talks. This method of alternating variables works very well in practice. Okay, MATLAB has a built-in thing, fmin search. That'd be fun for you to play around with. In that, I think there's an option to turn on an algorithm called Nelder-Mead. And I just want to talk about this one because I think it's super cool. It's like it's got a neat visualization, and it's just a wild way of thinking about solving an optimization problem. So we're going to form something called a basis of n+1 points when we have an n-dimensional problem. So let's say we were in the example, we have an x1 and an x2. So we're actually, that makes an R3 surface. And so we're going to form a basis of 3 points in that example. We're going to form something called the simplex, which is not the simplex algorithm, but when you take the convex hull of a number of points, that's actually called a simplex. So if I have 1, 2, 3 points, and I shrink wrap them, that is the convex hull. A convex hull around those 3 points, which in this case is a triangular region. That region is called a simplex. So when in n space, if you take n+1 points and you shrink wrap them, that's a simplex. A mathematical term that existed long before the simplex algorithm. Okay, and the idea of if I have these 3 points, I'm going to move away. I'm going to evaluate all of them. So just like that function evaluation we did on the first slide, take those 3 points, plug them into the function, see what their objective function value is. And I will move away from the worst of those points and get a new point. So in n = 2, you'd have a basis of 3 points that live in the xy plane, and therefore the simplex will be a triangle. And we'll create a new simplex. So we'll have in the xy plane, so imagine this is the xy plane here, 1, 2, 3 points. That makes a triangle. Say this was the worst one. I'm now going to keep these two and move away from this one somehow by creating a new simplex. So I'm going to get one more point, say that's over here. Now I have a new simplex, that triangle. And I'm going to keep doing that. And there's the Nelder-Mead algorithm created by these guys, does four main steps. It reflects, expands, contracts, or shrinks the current simplex to get to a new one. So here's a visualization. If I had these points here, here is a reflection, 1, 2, 3 points, and I've reflected to get to a new point. So I kept these two. I got rid of this one. It was the worst one. I moved away from that and got this third point. And now I've reflected. That's the action of reflected. Or you can do an expansion step. I have these three initial points. I wrap them in a convex hull, makes a simplex. I'm going to actually reflect and expand. So I'm actually going to go past that reflection point to an expansion point. That's my third point, new third point, and this is my new simplex. Let's see, a couple more. You could, they call it an outside contraction or an inside contraction. So that point actually got contracted to here, where you can shrink. So these three original points and shrunk down to here. All right, let's watch what actually happens in R3 on a surface. So again, what's really happening is so here's some surface, and it gets a little weird down there at the point here. We'll see as we zoom in, it's not quite a paraboloid, it's got a weird little point down there. But below that is the XY plane, and the 3 points live in the XY plane. Those 3 points, though, are evaluated up on the surface. So there's actually a triangular simplex that's going to move on the surface. So let's watch what happens as we go through some iterations. So we were up towards the top, and then Nelder-Mead makes this shape, and then here's another triangle, and then it flips all the way over to here, and then it flips to here, and then these three, and then these three, and it keeps on until it gets down into this. Again, like I said, it gets a little bit weirder. Goes from this point, and so you see more surface. What's actually happening on the contour map? Maybe you started over here with this little triangle. That's your initialization, and then at step one iteration, you've flipped, reflected all the way down, and these are your 3 points. So that was the first iterate. Now I'm down here. Step 2 here. Step 3, and then jump ahead, step 7, and step 12. So again, we're doing this. I don't know if you guys are probably here, but there used to be in the cereal boxes when I was growing up, you could get something called a wacky wall walker. This was a rubberized thing that kind of looked like a spider or octopus, had a little body and some legs, and you could throw it at the wall, and it would like stick and then slowly come down the wall in this motion. And that's kind of what Nelder-Mead reminds me of, this wacky wall walk down the surface, doing these reflections, contractions, flipping, expansions, all about the surface. Oh yeah, and this one, in this instance, it took 30 iterations till the convergence criteria, that one iteration to the next hadn't changed by some amount. So that's a common criteria, and we talked about that with the interior point method. You look at xt and xt plus 1, take the difference of those and the norm, and if the norm of that is less than some tolerance, like 10 to the minus 8, okay, that's close enough, we're good, we've converged. Okay, Nelder-Mead, super cool, but not proven to converge in general. It is widely used though, very easy to implement, inexpensive, only takes a few function evaluations per iteration, not have to compute any gradients, no derivatives needed. And it tends to make really good progress at the beginning. Where it's weaker is it slows down towards the bottom when it gets closer to that end. So here's something you can play around with. You should go into MATLAB's fmin search, take a look at the options so you can display the iterations. They have some samples there, use some of their sample functions. And I think there's ones where it might, if it doesn't come standard in fmin search, certainly someone has made a code or M file to actually visualize that, like we were doing a few slides back, right? Visualizing it, doing the wacky wall walking down the surface. So if you pick an example in R3, you can visualize that. Okay. Last thing, and we will talk some more, I think I have another talk on this, on genetic or evolutionary algorithms. So often they're called evolution optimization or genetic algorithms, GA or EO for the short for that. And we'll talk some more about that. So I think I'll just say that it's a idea built off evolution and how survival of the fittest and the best or fittest survive. So we're actually going to keep a population of possible candidates. And you can think population, like Nelder-Mead actually kept a population at every iteration. It's considering 3 things. So you can say it has a population of 3 solutions that it's considering and then making improvements based off that. Well, genetic algorithms and evolution optimization do the same thing. They might keep a population of 10 or 100 solutions that satisfy, live in the feasible region, and they will mate and mutate them to get to a better solution. So we're going to talk more about that next one. All right, we'll have fun playing with F-min search and Nelder-Mead.